Today we want to introduce something kind of new. It's related to what we've been doing with potential and kinetic energy, but goes by a different term here. It's called work. What's work? Work is defined as the change in energy experienced by an object. So if a car gains energy as it speeds up from the stop sign to 100 kilometers per hour, the work done is the change in energy experienced by that car. If a rock falls from the top of a cliff, the change in energy experienced by the rock, the energy gained by the rock as it falls, is equal to the work done on the rock. If the car comes to a screeching stop at a stoplight, then the work done on that car is equal to the loss of energy of that car. So work can be a gain of energy or a loss of energy. In general, work is defined as the change in energy experienced by an object. Now, in order to change an object's energy, there are two things that are required to be done. You can't have work done, you can't have a change in energy without both of these things being done. Let's look at the desk up at the front of the room here right now. How much energy, Nick, does that desk have at the front of the room? It's sitting on the ground, it's at rest. Zero. It's got 0 joules of energy. No potential energy, well, at least relative to the ground, it has no potential energy. Can't fall to the ground because it's already on the ground. It's not moving. It has no kinetic energy. It has 0 joules. Now, I want to give it energy. I want to change its energy. In other words, I want to do work on that desk. What do I got to do to it? What do I have to do to that desk in order to do work on that desk, in order to get it energy that it doesn't have right now? Good, Laura. I got to push it, right? I got to apply a force. This desk will never have energy if it isn't pushed or pulled, for that matter, right? Got to apply a force. The first thing I got to do, apply a force on the object. I'll push that desk right now. Am I doing work on it right now? Here's the real question. Am I changing the energy of that desk right now? Look at me. I'm pushing on it, not very hard. Am I changing the energy of that desk? Look at the desk. No. Its energy is 0 right now. As I push it, its energy is still 0. So a force isn't enough. It's needed. It's one of the two things that's needed, but it's not enough. What's the second thing that's needed? Oh, was your hand up? No? What's the second thing that's needed, Nick? Kinda. Yeah, kinda. Right? I'm pushing it here. I'm pushing in a particular direction. Force is a vector, so direction is important, absolutely. It's especially important, you're going to see a little bit later on. Kind of wait to talk about that, though. You there? Good. Now let's not be quite that specific. Instead of changing the direction of motion, let's just say motion. There's got to be motion. If you push it and it doesn't move, you're not changing its energy. But if you push it and it moves, it had 0 energy. Now it's got something as it's moving, right? Because I pushed it. So it's got a change in energy. We need to push it or pull it, and we also need to move it. It needs a force, and we need a displacement. Now, a couple of you kind of alluded to direction here and how direction kind of plays a role in this. Yeah, it does. Okay, force is a vector. Displacement's a vector. Direction is important here. Work isn't, by the way. Work's a scalar because energy is a scalar. But a vector times a vector gives us a scalar. There is some direction that comes into play here, and here's where it comes in. The force and the direction the force and the displacement need to be parallel to each other in order for me to do work on the object. So for instance, if this desk moves horizontally along the floor, then the force that I apply must be horizontal along the floor. Anybody curl here? Anybody a curler? Curling rocks will slide very easily down the ice because there's very, very little friction. Once they're moving, there's no work being done on that curling rock because we're not applying a force. There's displacement, but there's not force. So the curling rock moves at a constant speed. Its kinetic energy isn't changing. There's no work being done on the curling rock. If I all of a sudden step out and put my foot on a curling rock and push it down into the ice, but that curling rock keeps going forward and doesn't slow down, then what have I done? Nothing. I haven't done any work on it. Even though there's a displacement and I'm applying a force, if the displacement is this way, but my force is this way, I still haven't done any work on it because I'm not going to change its energy. If I want to change the energy of that curling rock and it's moving to the right, then I have to apply a force either to the right to cause the curling rock to speed up, or I can apply a force to the left to cause the curling rock to slow down. Either way, I've got to apply the force parallel to the displacement in order to change the energy of the curling rock. Somebody might be thinking out there, especially if you were a curler, sometimes I apply a force on the curling rock, not parallel to the way that it's moving, but maybe I put my broom down at an angle. The curling rock is going like this to the right, but I hold my broom down like this to stop the rock, and it stops. So the rock experiences a change in energy. The rock has work done on it, even though I'm not applying the force parallel to the way that it's moving. Or am I? Am I applying a force parallel to the motion there? What if I apply a force of 100 newtons and the angle is 60 degrees there? Am I applying a force parallel to the motion of this curling rock? Yes, I am. But it's not 100 newtons. What is it? It's 50, because it's going to be cosine 60 degrees. We'd have to find the x component, right? In other words, we'd have to find the component of that 100 that is parallel to the motion of the curling rock. Got it? So, in order to do work on an object, in order to change an object's energy, you need to apply a force, you need to have a displacement. The force and the displacement must be in the same direction. If they're 90 degrees to each other, hey, there is no work done. If they're at something other than 90 degrees to each other, then we have to effectively find a component of the force that is parallel to the direction of motion. The good news is, there's a general form of the equation that does that for me. Work is equal to delta E. But work is also equal to the force, because force is required to have work done, times the displacement. Remember what we said, though? Dom said that the x component there would be cosine 60 degrees is equal to adjacent over hypotenuse. So adjacent is equal to 100 cos 60. In other words, the x component is equal to the force times cosine theta. F cos theta times displacement is the work. The general form of the equation that appears on your data sheet already finds the component of the force parallel to the motion for you. Let's take a step back mathematically for a second. Curling rock is moving horizontal. I push straight down on the curling rock. What's the angle? 90. Am I doing work on the curling rock? No, because none of that force is parallel to the direction of motion of the curling rock, right? What's cosine 90? Do it on your calculator right now. What's cosine 90? Yep, 0. So what's F times D times 0? 0. I haven't done any work on it, right? 0 joules of work, 0 joules change in energy of it. All right, let's change this around a little bit. Let's say the curling rock is moving forward. I push it forward. What's the angle? No. Close though. Actually, it's funny, actually. You said 180, and I said close. You're kind of close, but you're kind of about as far off as you could possibly be. So what is the angle? Oh, what's the angle that's as far away from 180 as it could possibly be? No. Well, 360 actually would work because it's the same thing as saying 0, right? If I push it in a way that it moves, that's a 0-degree angle. If it's moving to the right and I push it to the left, that's 180. Either way, the angle cosine 0, cosine 180 is either 1 or negative 1. Listen, if you push it in the direction that it moves, you can actually cheat a little bit and take off the cos theta. Because if cos theta is 1, then F times D times 1 is just F times D. We're going to leave it on there for now. But I'll tell you that about 80% of the questions, the angle is going to be 0. So you can drop cos theta. Let me give you a couple of examples of when it may or may not be 0, and then we'll do a mathematical problem. Here's a wagon. The wagon moves to the right. I pull it at an angle of 40 degrees. Would I use F times D here, or would I use FD cos theta here? Yep, FD cos theta, because there is an angle between the way that it moves and the way that I pull it. Good. Here's a hill. Here's a wagon on the hill. The angle of the hill is 40 degrees. I'm pulling it up the hill. It moves up the hill. Would I use FD or FD cos theta for this one? Yeah. Good. Why? Why would I drop the cos theta? Yeah, it's moving at 40 degrees, but I'm pulling it at 40 degrees. So the difference between the way that I pull it and the way that it moves is 0. Cosine 0 is 1, so it becomes F times D. How about this one? Pulling the wagon up the hill again. The angle of the hill is 40 degrees. I pull it up at an angle of 60 degrees. F times D or FD cos theta? Jonathan? Yeah, good. F times D times cos theta. What would theta be? 20 degrees? Who thinks 20? Who thinks 40? Who thinks 60? The angle's 20. Jonathan, why is the angle 20? Yeah, I don't really care which way it's pulled. I want how it's pulled relative to the way that it moves. So if I'm pulling it at 60 degrees, yeah, that's great. It's moving at 40 degrees. It's only 20 degrees difference between the way that I pull it and the way that it moves. So that's the angle that I'd use there, 20 degrees. It would be rare, very rare, for you to get a question like that. It would. Even though it's not crazy hard, it'd be rare to get that. Most questions are going to be like this, where it's FD cos theta and the angle is pretty obvious, or it's just going to be a problem where it's F times D because the angle is 0. All right? Let's take a look at one quick example problem, and then we'll give you a couple questions to work on. That's going to be it for the day. Question says, figure 6.8, I should say, shows a force of 150 newtons at 0 degrees acting on an object that moves over a displacement of 25 meters at 25 degrees while the force acts. What's the work done by this force? F times D or FD cos theta? Matt, FD or FD cos theta? Good. Now, it's also good at delta E, right? But the delta E part isn't relevant here. It's FD cos theta. The force is 150 newtons. The displacement is 25 meters. Hey, if this was, let's say, 10 degrees, clearly the angle that we're going to use here is 25 degrees. But if that angle was 10 degrees, what angle would we use then? 10, 25, or something else? Tom? We'd use 15 then, right? The difference between the way that it's pulled and the way that it moves. Let's figure this out. We get 339.86 joules, which we're going to round actually to 3 digits, or 340 joules. Right? Just as an aside over here, okay, we're done that question. But just as an aside over there, what if I pulled it at 25 degrees? It moves at 25, I pulled it at 25. What's theta? What's theta there? Curtis? Cos theta is 1. Theta would be 0, right? So we just say W is equal to F times D in that case. Let's figure out what F times D is. 150 times 25? What's that work out to be? What do we say here, 3750? And we had a little bit of a typo over here, right? This shouldn't have been 339. This should have been 3,000. What was it, 3,000? So if we pull it straight, we pull it in the direction that it moves, the work that we do is 3,750. If we pull it at an angle, the work is 3,400. Does it make more sense that we're going to be more efficient if we pull it in the way that we're trying to move it? We're going to do more work on the object. Hey, if I want something to move to the right, I'm going to do more work on it if I pull it to the right. Trying to move a dresser across your bedroom floor to rearrange your room. Intuitively, we know to maximize the amount of work that we want to do, we're going to push the dresser in the direction we want it to move, right? It only makes sense. That's why this number is bigger than the other number. All right. Got a couple questions to work on here. I'm only going to ask you to do the first two, please, on page 294. We'll assign this for homework. You got a few minutes to work on them here now, but if you don't finish them, do them up for homework tonight, please.